Good morning all of you. Today we are going to discuss rotational mechanical systems. Okay, unit 1, subject control systems. Okay, so in the last class we have discussed a rotational mechanical system, mathematical modeling of rotational mechanical system. Okay, and their variables and elements. Okay, and for elements we are written torque equations, right, for all three elements, right? So in this case we'll see the torque voltage analogy and torque current analogy. So what do you mean by torque voltage analogy? Torque voltage analogy, see, whenever if we consider a rotational system, okay, so for that we are writing the torque equations, and that equations will be analogous to the electrical system, okay, to find the transfer function. Okay, so let us see the torque voltage analogy in this case. Okay, let us see torque voltage analogy. Okay, so it is also called TV analogy. So in the translational mechanical system, okay, what we did in there, force voltage analogy and force current analogy. Okay, while conversion of translational systems to electrical systems. Here also rotational system to electrical systems. Okay, now see, consider the following rotational system. So I'm writing directly rotational system, rotational mechanical system, that is, right? So see here, consider a system. So basic system I'm considering here. So this is the inertia element and this is the spring element, okay, which is connected here, and we have a ground here, and so this is a spring element, this is inertia element, and here we have a dashpot. Okay, like this. Now externally applied torque and velocity. Okay, so this is given rotational mechanical system. Okay, so let us write the torque equation directly here. So before going to that, let us see free body diagram. Free body diagram of given system. So simply, what is a free body diagram? It will shows applied torques and opposing torques. Okay, so what is this? This is externally applied torque, this one. Okay, and T torques is opposing here. See, this is opposing, so TK, and here also dashpot opposing TB, and this one inertia element opposing TJ. Okay, these all are the opposing torques. Okay, right, TK, TB and TJ. Okay, so this is inertia element acting on a inertia element. This is a free body diagram. So let us write the force equations. Okay, so by D'Alembert's principle, okay, so let us write the torque equations. Okay, so I'm writing directly here torque tau is equal to torque is equal to, now what is the right order wise, J in terms of velocity I am writing here, angular velocity, in terms of angular velocity, d by dt of angular velocity plus b omega plus 1 by k into angular omega t. Okay, so this consider as this is equation 1. Right, next is simple. Next is consider a series RLC circuit. Okay, so let us consider a RLC series network. So what is that? This is voltage plus minus volts, and here resistance, inductance, and output capacitance. Okay, so here RLC network, right? So current I is flowing in this. Okay, so anyway we have a drop here, voltage drop, right? So write the differential equations for this one by applying. So by applying KVL, okay, to the circuit. So what is the differential? Already we know this one, L di by dt plus inductance I written first, right? Next is I into R, okay, current through inductor, the resistance, and last one is 1 by C it dt. Okay, take is this is equation 2. Okay, consider this is equation 2. Now equation 1 and 2 represents, this is important here, equation 1 and 2 represents analogous system, since torque of mechanical system is made analogous to voltage of electrical system. See, already the same manner we completed translational mechanical system, force voltage analogy. Okay, so torque voltage analogy also we need to take the conversion TV analogous system, right? Okay, so write the equation side by side here. So I will rewrite the equations. So this is a torque equation, right? Torque equation. So what is that? T is equal to J d by dt of velocity, angular velocity you can say, don't forget to angular velocity, name angular velocity, omega dt. Okay, this is equation 1 anyway written in the top. Now another equation, second equation here we have available, L di by dt plus what is that, Ri plus 1 by C I dt. This is anyway second equation. Now see here, we need to take the comparison. See, in TV analogy, so let us write TV analogy. So we made a table here. Okay, right. So this is rotational mechanical system. This is electrical system, right? Now see here, take the comparisons directly. Torque in rotational system becomes analogous of V in electrical systems, right? So like that you need to take the conversion. Torque T, this becomes analogous in electrical system, becomes it is voltage V, right? Right. Now continuation, angular velocity. Omega becomes what? Angular velocity. Omega becomes what here in this case? Current. Current I. Right? Okay. Next is angular displacement. Angular displacement theta. Okay, this becomes what? Angular displacement. Okay, theta is not there, so angular displacement becomes in voltage is what? Charge. Okay. So okay, let's continue this one. Next is moment of inertia. Inertia element, or you can call it moment of inertia. Okay, this is nothing but J, capital J, right? So moment of inertia, this becomes here, see, this becomes what here? Inductance. So it is inductance in electrical system, L, right? Okay, sorry. Next is damper element. Damper element I am writing directly, or a damping coefficient here also, right? Damper element B becomes what here? Damper element C here in this case. Damper element B becomes what? Resistance in the electrical system. Resistance R in the electrical system. Okay, anything forgotten? Right. See, we have stiffness also. Stiffness becomes what? Capacitance. Spring element or stiffness, that is K, represents K. This becomes what here? Capacitance. Capacitance in electrical system. Okay, so this is a conversion of rotational mechanical system made of analogous electrical system. Okay, so next we will see torque current analogy. Okay, so let us see. Torque current analogy. Okay, so it is also called TI analogy. Okay, so let us use a torque current analogy. Now same process. Consider rotational mechanical system. Okay, so let us draw the system. Same system I am taking for convenience. Okay, so this is a spring element, right, which is connected to inertia. Okay, This is another graph, and K dashpot and inertia element, right? So externally applied torque T and angular velocity in the same direction. Now in this case, this is a given rotational system. For this we need to draw a free body diagram to write the free body diagram here. So this is J inertia element, so applied torque and opposing torques will be Tk, Tj and Tb as mentioned. So this is opposing Tk and here it is opposing Tb and this one is here opposing Tj. Okay, torques, right? So this is a free body diagram. So let us write the torque equation by D'Alembert's principle. Okay, so I am writing directly torque is equal to what is that? J d omega by dt plus b omega in terms of angular velocity. I am writing here 1 by k integration of omega t dt. Okay, take as equation 1, right? Now consider a parallel RLC circuit. Okay, so here consider a parallel RLC circuit. Let us see the parallel RLC circuit. So this is I of t or I. Okay, so this is resistance, this is inductance, and this one will be the capacitance. Okay, so here RLC network, right? So anyway, we have a drop it output, and here entering currents I am considering here I1, I2 and I3. Okay, so therefore see here writing the equation. So by applying KCL, okay, to the network, then I'm considering I is equal to so what I mentioned I1 plus I2 plus I3. Okay, so just write the KCL here. Therefore I is equal to C dV by dt, the order wise I am writing for comparison, V by R plus 1 by L integration V dt. Okay, so if I rewrite this one, or I can say I is equal to C d, it's capital you can write better, where voltage will be in capital. Okay, right, dV by dt plus 1 by R I am writing as a conductance plus 1 by L integration V dt. Okay, consider this as a equation 2. Okay, now we will compare equation 1 and 2 to make an analogous rotational system analogous to electrical system. Okay, now comparing equation 1 and 2, I am writing directly here. Now by comparing equations 1 and 2, so what is the first equation we have? So side by side I am writing here J d by dt plus b into omega plus 1 by k into omega dt. Okay, this is anyway our first equation, and the second one is this one. I is equal to, I am writing side by side here, I is equal to c dv by dt plus gv plus 1 by L integration v dt. This is a second equation, this equation, right? Now we will make a table. Okay, so now I am taking TI analogy. Okay, so you need to remember this TI. Okay, torque current analogy, this one, right? So let us make a table. Right here, rotational mechanical system, and this one is electrical systems. Okay, so let us see the conversion. Torque in mechanical system, torque in mechanical system becomes what here? Current I in electrical system, right? Next is we can say angular displacement or angular velocity. Angular velocity omega. Okay, omega is becomes angular velocity. See here, angular velocity becomes here voltage. That is in electrical systems, right? I will change the pen here. Okay, I'll write this same pen, no problem. Next is angular displacement. Theta becomes, see, angular displacement we are taking. So in the current, angular displacement will be, as we discussed in the previous class, flux. Okay, this is represented with pi. Okay, next is inertia element or movement of inertia, that is J. Okay, J becomes capacitance here. Capacitance in electrical systems. Next term is, you can say, stiffness. That is K. So what is the K value here? K is inductor. K is here inductance. Inductance L. Okay, in electrical systems. Anything forgotten? Damping coefficient you have. Damper element. Damping coefficient or damper element B. B becomes conductance in this case. 1 by R, right? Conductance. Okay. C R 1 by R. Okay. So this is the TI analogy or torque current analogy. Okay, of rotational mechanical system, right? So from this we'll make an analogous system from rotational to electrical system, okay, by writing differential equations, okay, and also we'll find the transfer function of rotational systems by writing the differential equations and by taking Laplace transform of the differential equations, and we'll find the output by input. Okay, so that is a, so let us see the example of rotational mechanical system. Okay, so we'll solve the problems here. So first example 1. Okay, so here is obtain the transfer function function of mechanical system and draw the analogous electrical network based on the first one, torque voltage analogy, and the second one, torque current analogy. Okay, so let us see. And the given rotational system is given here. So this is okay. So here connected spring element, and here it is connected another inertia element, and it is connected dashpot, and this is connected to ground. Okay. Right. Okay. So this is J1, J2, and here is a K, and this one is B. Now externally applied, here is the external applied torque. Okay, with the same direction we have displacement and velocity V1, and also here it is given in this case we have displacement 2 and velocity W2. Okay. So this is a given question, right? So let us find the solution for this one. Okay, let us see the solution. So given rotational system, okay, rotational mechanical system, we need to draw the free body diagram individually, okay, as we did in the translational mechanical system, same, right? So free body diagram for inertia J1. Okay, so draw the free body diagram here. So already we know the free body diagram represents, this is J. So free body diagram represents what? In this case we have applied torque, this one, see here, and what are the opposing torques here? Torques here, see here. For this particular diagram we have this one is opposing in this case, right, TK, and this is opposing TJ1. Okay, only two elements here, TK and TJ1, right? Okay, TK and TJ1. Okay, and externally applied torque is this one, right? So write the torque equation by D'Alembert's principle. So torque equation, okay, so by applying D'Alembert's principle, okay, so what is the torque equation? Torque is equal to J1 in terms of velocity you need to write. Okay, so I'm writing in terms of velocity, right, divided by what is this? See, first of all we'll find the transfer function. Okay, so for the transfer function we need to write the torque equations in terms of angular displacement. Okay, so I'm writing the torque equations in terms of angular displacement here. Okay, angular displacement, okay, that is theta, right? So here then d square dt by theta plus k. See here, spring element, this force, this particular one, spring, this particular one. See here, torque, can I write k is connected between, sorry, this is J1, right here J1, this is J1, right? So spring element is connected between inertia element 1 and inertia element 2, okay? Therefore the spring element depends on the angular velocity or angular displacement of theta 1 and theta 2, okay? So therefore how can we write this one? Theta 1 minus theta 2, right? So therefore I mention here theta 1 minus theta 2, okay, which is nothing but a reference inertia angular displacement minus other inertia angular displacements, okay? In this case reference one means what? Free body diagram I drawn for J1. This is our reference inertia, right? Okay. Now consider this as a equation 1, right? Okay, so I would like to take Laplace transform here only, then we name it that is as a equation 1, okay? So by taking Laplace transform, okay, so let us take Laplace transform for this one. So this will become T of S is equal to inertia element J1 into this is S square, and this is nothing but, so here theta 1 is, okay, so theta 1 of S plus in this case K, okay, directly I will write here K 1 of S minus theta 2 of S, okay. Now I'd like to minimize this one, so T of S becomes J1 S square theta 1 of S plus K theta 1 of S minus K theta 2 of S, okay. Now consider this as a equation 1, okay. Right, so next I would like to draw free body diagram for inertia J2, okay. Let us go to the diagram once. Here is a J2, so okay, so inertia J2, what are the opposing torques here? See here, so this one is opposing torque here, TK, TJ2 is opposing torque, TK again it is connected between J2 and J1, so TK is opposing here, okay. Again this one is opposing, what is that? TB, right? So here in this case, see here the dotted lines, see there is no externally applied torque connected to inertia J2, right? So externally applied torque becomes 0. Right, let us draw the free body diagram. This is J2, okay. So all are opposing torques only here. We have TJ2 and we have TK, and another one we have TB, okay, due to these elements. Okay, torque is opposing here, right? So this is a free body diagram. So let us write the torque equation. Okay, so by D'Alembert's principle, so writing the torque equation, there is no external torque is applied. Okay, so I can write let's see this one, T J2 plus T B plus T K. Okay, so therefore I will write this one. So J2 into, so we are writing the differential equations or torque equations in terms of angular displacement. So d by dt square, okay, theta 2, okay, plus here dash part b into, see in this case dash part is connected to ground. I think in the diagram, see here dash part is connected to ground directly. Okay, so only theta 2, it is depends on the angular velocity theta 2. Okay, so it is nothing but d by dt of theta 2. Okay, plus k value, k, see in this case k is connected in between. Now this time our reference inertia will be J2. Okay, so first we need to consider J2, then J1, which is nothing but theta 2 minus theta 1. Okay, sorry. Okay, now like to take Laplace transform here by taking Laplace transform. Okay, so this one will be J2, okay, s square theta 2 of s plus b into s theta 2 of s plus in this case k into theta 2 of s minus theta 1 of s. So like that is equal to 0. Sorry. Right, okay. Now I will rewrite this equation. J2 s square theta 2 of s plus b s into theta 2 of s plus k theta 2 of s minus k theta 1 of s, okay, is equal to 0. Consider this as equation 2. Right, now so in this case what we need to find, the transfer function should be theta 2 of s divided by t of s. Okay, so this is output and this is this equation here. So let us see. So take common theta 2 of s. Okay, so let us write the equation. J2 s square plus taken here theta 2 of s common, okay, and here s into bs you can say, okay, plus here k, okay, theta 2 taken common minus k theta 1 of s is equal to 0. Still minimize this one. So theta 2 of s into J2 s square plus bs plus k is equal to, I am taking this side, okay, k theta 1 of s. Okay, now this can be written simply theta 1 of s is equal to theta 2 of s J2 s square plus bs plus K divided by K. Okay, so consider this as equation 3 now, right? Now substitute equation 3 in equation. Rewrite equation 1, that is T of S is equal to J1 S square T1 of S plus K T1 of S minus K T2 of S. Okay, so this is, we have equation 1. Okay, minimize this one, or I can write this one, T of S is equal to, if I take common, theta 1 of S. Okay, so I would like to take that outside. Theta 1 of S becomes J1 of S square plus K minus K theta 2 of S. Okay, now substitute in the above equation in this equation, now present equation, right? So therefore see here, T of S is equal to, substituting theta 1 value here, right? So theta 2 of S into J2 S square plus BS plus K divided by K into J1 S square plus J. Okay, total minus of K theta 2 of S. Okay, now T of S is equal to, now take cross multiplication, this is theta 2 of S, right, into the same value. This is considered as a 1, so this is nothing but K J2 S square plus BS plus K into J1 S square plus K. Okay, minus, in this case, K square theta 2 of S, right? Now take the common theta 2 in this case. Okay, so what is the transfer function you have? Transfer function is nothing but theta 2 of S divided by T of S. Okay, therefore I'm writing the equation here, above equation, Ts is equal to theta 2 of S, take common this one, enter term K, and this one will be J2 S square plus BS plus K into J1 S square plus K, J1 S square, right, minus K square. Okay, now find the transfer function, becomes, now in this case, theta 2 of S divided by T of S. It's nothing but transfer function. Okay, so this is given by, so enter term K divided by the above term, this term, right, J2 S square plus BS plus K into J1 S square plus K minus K square. Okay, this is our transfer function. Okay, so this is our final transfer function for given rotational mechanical system, right? Let us draw the electrical analogous circuit of given based on TV and TI. Okay, right, the first one is, so we would like to take TV analogy. Okay, so transfer function is completed. Next is TV analogy. We need to draw analogous electrical circuit for given rotational mechanical system, right? So So in the TV analogy, okay, you have to remember compulsory. So torque becomes what? Voltage. Velocity becomes angular velocity becomes what? Current. And displacement, angular displacement becomes charge, and inertia element becomes what? Inductance L, and dashpot becomes what? Resistance, and spring element becomes capacitance. Okay, so you need to remember this all. Okay, this analogy you need to remember, then only will make analogous system conversion, otherwise not. Okay. Now, so quickly I will redraw the rotational mechanical system, given rotational mechanical system. Let's see here. And here a dashpot is connected, so this is the reference. Okay, so here is J1, J2, K, B. Okay, and here external torque is applied as a angular displacement, angular displacement. Okay. So this is the equations given, right? So here you can write angular velocity 1, angular velocity 2 also. Okay, so this is given mechanical system. For this we need to draw. So what is the procedure? So this is mechanical network, right? Diagram. For this we need to rearrange the elements and draw this mechanical system in terms of electrical form. Okay. So let us draw analogous electrical network. Okay, so before going to that, see, I am considering this as a velocity 1, consider another node here, velocity 2, okay, and consider another one here, ground. Okay, so with these references we'll draw, right? See here, so whatever I am drawing, this is rearrangement of mechanical network. Okay, so rearranging mechanical network here. Okay, so see here, as it is I am rearranging here, this is torque T, and we have a see, this J1 is connected to ground with velocity, angular velocity V1. Okay, so this is point where we have angular velocity node. Okay, from this node J1 is connected here, right? I'm naming it J1. Okay, and this is, we have a ground G and D. Okay. Now this is connected as it is, right? And from here I'm taken a node, angular velocity node V2, so this is J2. Okay, and grounded that one. Another one also grounded, that is what we have, damper element. Okay, so this is the rearrangement of given mechanical, rotational mechanical system. Okay, now we need to take, from this we need to take TV analogy, TV conversion. Okay, so let us see the TV conversion. Now what I said, from this side only I am starting. Okay, whatever the elements, okay, we need to convert the elements, the rotational mechanical system to electrical mechanical system, and parallel become series, series become parallel for torque voltage analogy. Remember this one, I am repeating. Okay, while drawing the electrical network, okay, from the rearrangement of mechanical network, convert the elements of mechanical to electrical, and also whatever the elements present here, right, series become parallel, parallel become series, you need to draw. Okay, so okay, right. So you need to remember all these things. See here, so torque become voltage, Okay, inertia becomes inductance. Okay, you need to consider this all, right? So torque become voltage plus minus voltage. Okay, T is converted as voltage here, and this network will be, see, in this we have inertia element as a parallel, so that one we need to write in series. J1 becomes what? L1, right? TV conversion, this is L1, right? Now here K, this one, okay, K is connected in series. Now we need to draw that one as a parallel. K becomes what here? C. Okay, while converting, that is C. And again J2, it is in parallel, then we need to draw that one as in series. Now this is also parallel, then we draw that one. So this is B. Dashboard B becomes resistance, conversion resistance. Okay, now this is our final network, which is current I1 and this one current, say, I2. Okay, so this is the resultant electrical network. Okay, resultant electrical network. This is TV, right? Torque voltage analogy. Okay, now we'll see the torque current analogy. Okay, torque current analogy conversion. Okay, so we'll draw the networks here. So for this one we need to draw the rearrangement of mechanical system. Whatever we drawn, rearranged mechanical system again, or network. Okay, I'm redrawing that one from the above. Okay, same network. This is torque and right, this is J1 and this is spring K and this is J2. As it is, I am writing this is damper element, because to draw electrical network of conversion torque current we require this one, right? This is K, this is B, right? It is grounded and I named it, this is velocity, angular velocity V1 and angular velocity V2. This is ground. Okay, so this is velocity V1, V2 and ground. Okay, now so whenever we are converting torque to current, okay, then same network you need to draw with the replacement of elements. That's all, simple. Okay, so what is that? I'm redrawing here, so I will redraw here. This is, see, conversion you need to do. Torque becomes current. Okay, okay, torque become current and same as it is in right. J becomes, I mean inertia becomes capacitance, so which I will write C1, and inductance becomes, I mean K, spring element becomes inductance. See the conversion, you go through the conversion, and J2 becomes C2 and B becomes what? Conductance. This is G, conductance. This is a given network. Okay, so this is a node velocity V1, this is node velocity V2, these two nodes, and this is say ground, connected to ground. Okay, here also connected to ground. So this is the resultant network. Okay, in this case currents flowing is, this is I1, so this is right. Okay, so this is the completion of the problem. Okay, so just a small review. for given problem, from the angular displacement, okay, we find transfer function of given rotational mechanical system, and also we draw analogous electrical circuit, okay, of Ti and Tv. Okay, that means torque voltage analogy and torque current analogy. Okay, right. So this is the completion of unit 1. Okay, so in the next class we are going to start unit 2. Okay.